Hello world, it's me. In the last video, I went over enough of the history of the Fairchild F8 to know how the world got to this little Mostek 38P70. Now in this video, we're going to go and be looking at the processor and learn just enough about the processor so that we can start thinking about our real-time clock project. Of course, we're eventually going to need to know a lot about this, but right now let's just look at the basics so we have an idea as to how we can get things going, but also that'll tell us how many bells and whistles we can add to this project before we run out of capabilities of this little F8. For the most part, we aren't going to get into any of the programming of this F8 because that's where things really start to get weird on this chip. So here we are armed with the Mostek F8 catalog that details the 3870 family. We've got a blank sheet of paper here if we need it. And for inspiration, we have Will's 38P70 that he contributed to the project. So remember I introduced Will in the last video as the impetus for this whole project. And you can get a copy of this 81 Mostek 3870 data book on BitSavers. And if you're going to do this project, if you're going to want to make one of these boards or follow along, it's worth downloading and get a copy of this off of BitSavers. First, go over the pins and their functions to get a rough cut as to what features should be in our real-time clock. We can see it's got 40 pins, but 32 of these are I/O pins, so right off the bat, that's really convenient because it cuts down, the problem to size. There's only 8 pins here that do all of the control, so it can only get so complicated with just those 8 pins. So let's go through those 8 pins first, and then we will save all of the I/O for later. We can see right off the bat that 2 of them, crystal 1 and 2, are for the time-based input. And there's a number of ways to provide the oscillator for this 3870. It ranges from RC circuits, you can apply an external TTL signal, or you can simply connect a crystal and let the internal driver take the reins. And I can't think of a reason to overcomplicate that, so I hope to just plan on using a standard old-school crystal. The data book here recommends using a 3.58 megahertz crystal since they say it's widely used for the TV color burst. Probably not quite so much anymore, but I know we can still get them. I might even have some. But from the AC characteristics on page 90 here, we can see that we just need a crystal between 2 and 4 megahertz. So it does have a minimum frequency. So anything between 2 and 4 megahertz crystal will work fine. Of the remaining 6 pins that are not I/O, 1 is ground and 1 is VCC. Now VCC for the 3870 is just 5 volts. So this is a single rail chip, just 5 volts in ground. And it says here the user can either specify a 10% power supply tolerance or a 5% power supply tolerance. And I'm not exactly sure who gets to specify that, but in either case, it's not very stringent. Okay, while we're on this page, let's also look at the test pin. Conveniently for us, the test pin is left unconnected or grounded in normal use. So of the 8 pins that we started with, we're already down to only 3 left that we don't know about. Those are the strobe, the reset, and the external interrupt. Shouldn't come as a surprise to anyone that the reset pin will put the processor in a known state, which in the 3870 sets the program counter to 0, and when it's released, the 3870 will fetch its first instruction after exiting the reset state. A couple of things here are important. So here's a description of the external reset and what all it does. The program counter is pushed to the stack, and then the program counter and the ICB bit of the status register are cleared. ICB is the interrupt enable bit. So the interrupts are disabled following a reset, which, as we would expect. We can't do a reset and immediately let this thing go off to service an interrupt. They tell us the original stack register content is lost, so that's not a big deal for us. So it's completely cleared anything that was in the stack. And, I suppose not having to manage the stack cuts both ways. We don't have to worry about it, but then it's also out of our control. So we just know that when we do a reset, we've lost what was in the original stack. It goes on to say that ports 4, 5, 6, and 7 are loaded with zeros, but, and this is important, the contents of all the other registers and ports are unchanged or undefined. And this is really interesting because that means that after a reset, the first 2 I/O ports are undefined if it's a hard reset or a cold reset, like a power, say after a power cycle. But if the processor has already been running and it's then reset, the values of ports 0 and 1 are whatever they were before the reset. And I can see that being handy if we had a system where we had a watchdog that, could initiate a reset, and we wanted to know what those ports were. But for, our little real-time clock, I don't see that as being anything that we need to deal with. So let's just move on. The rest of this paragraph is way above our needs for our little real-time clock. Again, it's more about if you're trying to rescue the previous state after a warm reset occurred in mid-instruction. So more detail down here as to what happens if a reset comes in when it was just about to execute another instruction. But there is one more thought on this, and we need to consider that even if we've never written a bug in our software, we need to take extra care with ports 0 and 1, because ports 4 and 5 will wake up set to 0. And you've always got to remember on this 3870 that the ports are inverted. So if you output a 0 to the port, it's actually logic 1 on the pin. And with ports 4 and 5, that means that if it's open drain or if it has the internal soft 6K pull-up resistor, then either way the output will be floating or it'll be softly pulled up with that resistor. But the important point is that it's not actively being driven low, and that means that if we're using that pin as an input and it's being driven by another device, then that device is free to drive the pin high or low without a problem. Because when we did a reset, that pin is essentially floating as far as the processor is concerned, so we can do an input. Now, fortunately, as we'll see later, the piggyback devices did not have the direct drive option on these ports, so we know it's either one form or the other. It's either the open drain or it's the light pull-up, so meaning it either has the internal pull-up resistor or it doesn't. So the same cannot be said for ports 0 and 1. We know that those are standard output. If they happen to wake up set to 0, then they're floating just like ports 4 and 5, and there isn't a problem. But if a pin wakes up set to 1, so it's actively driving that output pin to ground, and we happen to be using that pin as an input to the processor that's being actively driven by a device, somewhere else we've got a gate somewhere that's driving that pin, and if that gate is driving that pin to a logic 1, so that external device is trying to drive this to 5 volts for all it's worth, while the 3870 is trying to pull it to ground. We need to be more careful with ports 0 and 1 than we do with ports 4 and 5. We really need to consider what happens on a power-up, and these outputs are unknown on ports 0 and 1, and they may actively be pulling the pin to ground. So we need to be a little bit careful as to how we use pins 0 and 1, at least much more so than we do ports 4 and 5. And that's just if we don't write any software mistakes. Now, if we have software bugs in here and we accidentally cause a pin to go in contention, then that's a separate issue. But at least on reset, we know what their state's going to be. Here on the two finalists, we've got the strobe and the external interrupt. Now, the strobe line is an output pin that's used for handshaking when data is moved out the I/O port 4. Executing an output instruction, the normally high strobe will go low after valid data has been presented at the output pins. And the idea is that if you've got something out there that you're going to latch the data from port 4, then rather than have to send out another signal to latch the data, the 3870 automatically toggles the strobe line to set your latches for you. And here it tells us that either edge of the strobe can be used to latch, meaning there's sufficient setup time before it goes low and there's sufficient hold time after it goes high. So we can either use a negative edge, a low level, or a rising edge trigger on that latch. I'm a bit confused by this next statement. It says the strobe may also be used as an input strobe to port 4 after completing the input operation. I think what they're trying to say is that you could use this as an acknowledge so that if you're sending things into that port, you can set up data, and then when the port has latched that data, use the strobe as an acknowledge that the input cycle is completed and that you can set up the next set of data. But it doesn't tell us which edge of the strobe is used for that latch, and in fact it doesn't, if you look at the timing diagrams, it doesn't even show that strobe as being asserted on an in instruction. Okay, I was curious enough about that to go look it up, and none of the timing diagrams seem to mention the port input triggering a strobe cycle. So I did a search for strobe and I went through all of the hits on that, and I found here on page 105 what is another hint, and I think this is what they were saying before. I don't think the way I interpreted it before is exactly what they mean. If we look ahead, this is for the 3873 version of the chip. And they say that the strobe provides a single low pulse, and we know that already. But it goes on to say the strobe may be used as an input strobe, meaning unacknowledged, just like they were saying before. But they go further and they say by doing a dummy output of 00 to port 4 after completing the input operation. So all they're saying here is that, but if you're doing an input, if you follow that input instruction with an output instruction, it then cycles the strobe line, and so you can use that as an acknowledge. So you're just going to have an instruction that says in from that port, you're then going to clear the accumulator and do an out instruction to that port just to get that strobe to go low and give you essentially a acknowledge. So that's a long way around to just make an acknowledge signal. But at least we know what they mean by that. It's kind of a common theme in this data book to make you dig for things. By the time you find something, you feel like you really deserved to know the answer. The last thing to know about the strobe is that it's essentially a hard direct drive. So don't mess around with it because it'll burn itself up trying to drive the output high or low. In the 3870, there is this little 1K that wasn't there in the 3851, so it's a tiny bit of protection. It says it can drive 3 full TTL loads. In the DC characteristics, it puts a finer point on that. It says the strobe can source either 270 or 300 microamps, depending on which one it is, and it can sync 4.5 or 5 milliamps, depending on the chip dash number. All right, the final line is the external interrupt, which is an input pin that can be used in a couple of different ways. One is as an external interrupt, and the other is associated with the internal timer on the 3870. We'll dig into this a little later in the project as needed, but it's a little deep for this first introduction, and I'm not sure we're even going to use the external interrupt pin at all in this project. It depends if we decide to put a real-time clock on this, and we're going to use an output from that to interrupt this, but we'll have to see what we do in the end. But I'm not sure we're even going to use the external interrupt. So we're at a good point. I think we already know a lot about this chip, maybe enough to avoid the most obvious mistakes when we're dealing with the control pins. But now let's go back and let's look at the I/O pins. Now let's look at port type. So the hardware type of port that when the masked ROM was ordered, the customer needed to specify the type of port. And there were 3 types. There's the totem pole output, but also had readback, so it could be an input and give you what the status of that pin was. So if you wanted to use that as an output, you just drove it. If you wanted to use it as an input, you let it float, and then whatever was driving that would have to pull the pins down. The next choice was an open drain, and that didn't have a pull-up resistor or a pull-up transistor, and it could only pull down the output pin, so the engineer needed to have a pull-up resistor somewhere else in their part of the circuit. And the third was the hard drive. It could drive it both ways, and it didn't have a readback at all. So you set that, you didn't know what it was doing. The only kind of readback it has was, if other than sending out the smoke signal, it would send out if it were accidentally connected to a equally hard drive circuit. Fortunately for the 3851, we have the preliminary documentation and the final documentation for this port. The preliminary one is actually a little bit more clear. If you look at the standard pull-up configuration, they've got 2 different diagrams here, one TTL to F8 and one F8 to TTL. Their intention for an input, when this pin is being used as an input, their intention is that the TTL driver should only be open collector. But I have to wonder if this diagram for what's inside the F8 is meant to be literal, or if there is some kind of protection on that pull-up transistor inside the F8. Because if you have your open collector pulling this down, and it truly has this high transistor trying to pull that totem pole up, then you can drive a lot of current through that. And of course, that open collector pull down is going to win. So there must be some kind of protection that's just not shown above that, between the rail and that pull-up transistor. For the 3870, there's still 3 port versions that you could order on the custom ROM, but the standard output was slightly modified. I suspect there may have been some damage done to many an output pin, so there's really just 2 versions of the configuration or open collector, and one is the hard drive. The hard drive is nearly the same as before, a pair of strong FETs to drive the port either way, but for protection, a little 1K resistor has been put into that hard drive to slow down any damage due to contention on the output. Likewise, for the standard output of the drive-up transistor, it's been completely removed and replaced with a 6K resistor. So instead of being a totem pole output, this is essentially an open collector output. the only difference between these two is whether that pull-up resistor is built into the chip or whether you have to provide it outside. So the only one that's actually the same as it was before is the open drain version. And when the customer ordered their custom mask 3870, they could specify buffers on ports 4 and 5. 0 and 1 were always the standard type. Of course, this also goes back to the first generation F8, where ports 0 and 1 were in the 3850, and the 3850 wasn't customized. Only the 3851 was customized. And while the customer could order whatever port style they wanted for ports 4 and 5 in the custom ROM version, in the piggyback version, only the standard output and open drain output are available. The hard drive version was not available for ports 4 and 5. Now, furthermore, in the piggyback version, all pins of the port were the same. In fact, in the piggyback version, all pins in both ports are the same. They were either all standard or they were all open drain. So how do you know which one you have? And this is one of the many critical details that, Mostek lets you go hunting for in this, but you feel somewhat rewarded after you find it. They made no extra effort to make this known, but there is a figure in their catalog that tells us, that, and it also tells us one other little crucial bit of information. On page 84, figure 7, it shows us that the two versions of the piggyback chip, in addition to the MK38P70 number on the top, there's a second number that begins as MK974 something something. And if it's a 97400, then the chip has a standard output. And if it's a 97410, then the chip has open drain outputs. And what we have here in Will's chip is a 97400. So this chip has the standard outputs. So it's got that little internal pull-up. But this figure also tells us which EEPROM can be used with the chip. And in this case, they both happen to be the same, but this isn't information that was necessarily easy to find in this catalog. The chip can utilize any of these four EEPROMs, the 2758, the 2716, the 2516, and the 2532. So the chip can access, the 3870 can access 4K of ROM if you happen to deal in 2500 EEPROMs, which I do not. But you could make an adapter if needed, or I suspect the gaming hardware guys already have adapters made for these pre-standard PROMs that have different pinouts on the chip selects and addresses. But I'm just going to plan on using a standard 2716 EEPROM because that's what everybody's going to have and that's what everybody can program. Oh, and before I forget, when inserting the EEPROM, it has to be bottom justified. So we're all used to that now, that if we're using these universal sites, the EEPROM is bottom justified. I know that some don't like my design of design and build rather than design, test, and build. And at one time I really enjoyed breadboarding and wire wrapping. I never really liked doing point-to-point solder breadboard, but I enjoyed perf board and wire wrapping. In fact, I liked it a lot. But I just don't enjoy those anymore. And now, PC boards are so incredibly cheap. I have so many projects going on at one time. I don't mind doing some design stuff and then sending off boards to be made and finding my bugs when they come back. So I wouldn't be surprised if when we are doing this clock chip, if we find some bugs in it. And of course, it's not to say I don't like bugs. If you see something in my designs that is not going to work, you shouldn't keep it a secret. Let me know. But I would just rather spend my time on writing software, doing board design and layout rather than wire wrapping. And I've learned that when a board comes back and it has bugs, I just don't sweat it if I need to spend a little time on another revision. In the grand scheme of things, retirement's really just running out the clock anyway. Before we end this video, I wanted to let you know what I'm thinking about in components for this real-time clock. So I went around and I looked at my bins and gathered up some of the things that I have. And one of the ones I wanted to look at first was the display. Now I have a bunch of these. They're LRT 1704. And I think they're about the same as the TIL 305. They're a 0.3-inch 5x7 matrix. I looked them up. They seem to be readily available for a few dollars each. And, this may very well be one of the last boards I breadboarded. This has been sitting in my bin for many, many, many years. I don't even remember what this board did. But here's an advertisement for that chip from 1979. So I know they're age appropriate, but I don't want to have to include a matrix decoder and drivers and so forth. And we could have the 3870, directly run those, but I'm not sure how much horsepower we would have in this, how many digits we could display. So there's a lot to go wrong. I really love this chip. I really like the look of it, but I'm not sure that I want to go there in this project. I think I want to do something quicker since I'm just kind of slipping this project in anyway. I've also have a bunch of these TIL 311 hexadecimal displays. About the same size. The data sheet I have for these is from 1972, so I know these are age appropriate. They came out even before the 3870. The big advantage of these is that they're latched, so the processor doesn't have to continuously drive it like these matrix ones. The processor can just send the data out and latch it and then go on to something else. So it doesn't have to do display maintenance once the data is latched into this display. So these would be convenient that we can just write them, use that port for business, write out to the display, decode these, and latch for each of them individually. So that would be a fairly easy one to use. And I also like the look of this display. And this is hexadecimal. Now the other ones that I have are these little electronics globe lens magnifier displays, like what you'd see in calculators. Or even, I think I had a watch one time that had a small version of these little globe lens magnifier displays. I think electronics introduced these in the late 70s, so again, they're very age appropriate. And the nice thing about these is they're intelligent, so it's easy to control many displays with one controller. And this would be a great application for intelligent displays. I have a whole bunch of these sitting in, I've got a couple of tubes of these. This would make a nice looking system. They've got 4 little digits. I looked on eBay. They seem to be available for a pretty modest cost. They certainly have that 1970s calculator feel to them. My first calculator had these kinds of displays in it. Each display has 4 alphanumeric characters. So that would be, a bit of a step up. So instead of just the 5x7 or the hexadecimal, these are actually alphanumeric. You just give it an ASCII character and it'll display it. So the nice thing about that is, in addition to a clock, we could make a little reader board effect on this. The only downside of these is, they're fairly small. They're only 0.16 inches high. And that's the magnified size. That's what they look like when you're looking at the through the globe. I'm not sure how big they actually are on the chip. But they only look like a 0.16 inch display. So that's pretty small. It's readable from quite a ways away, at least from the nightstand. I'm not sure if they're readable from across the room. Depends on how good your eyes are. Now, there was also the smaller 14/16s, and then there were the bigger 34/16s. Now, the smaller ones were only 0.11 inches high, where this is 0.16, I think, and then the larger ones were 0.225, so almost a quarter of an inch high. So any of these displays would have, the perfect aesthetics for this little clock project. I like the flexibility of these 24/16s because we're not limited to just hexadecimal. I like the idea of being able to have a full alphanumeric display and, maybe using this like a little reader board. These are, 15 or 18 segments, I forget exactly, but they make a pretty decent character. That would give the clock some great flexibility. We could use this board for a lot more than just a clock then. As for inputs, we want to have a couple of push buttons to set the clock. And I think I would like to do a BCD rotary encoder like I did on my, this is the bus monitor for the SBC project. And so, this is a little BCD encoder on the side. We could put a decimal one in, and it doesn't matter if it's decimal or BCD, I guess. And you could sit here, and it's got the nice little peg on it. And so with a little stem, you can turn it. It's easy to grab and turn without a screwdriver. So we could have a button that selects the digit, and then we could, just turn this to select the character in the digit. And then press the button again to select the next digit. So I think I want to have a little rotary switch as well as a button. Now, also looking at these just 7 segments, this wouldn't look bad with just a straight 7-segment display. But I think, any of these have a lot more panache. I'm liking these rather than just a straight segment. Plus, I don't have to have the drivers and everything if I use this intelligent one. And we need to have a little speaker here so that we can, turn this into an alarm clock and have this thing make noise as well as lights. And finally, I think I want to put a serial port on this. And the only thing I'm torn about is whether I should just drop a Max 232 on it. But the problem is the Max 232 isn't really period appropriate. Or should I go with traditional 1488, 1489 RS-232 drivers? Old school would mean having to provide 12 volts to this board, and I really don't want to do that. The Max 232 didn't come out until the late 80s, so it's a decade after all the rest of this stuff. And you would only need that 12 volts if you're using the serial port, and mini current adapters are perfectly happy with lower voltages anyway. So I have to make that decision. And finally, as I mentioned earlier, I may want to put a real-time clock on this. I need to see what real-time clocks were available in the late 70s to make sure I don't stray too far away from that decade with the components. And depending on other things, I may run short of pins if I put on a parallel clock, so I might need to have a serial real-time clock for this. So I need to pick out a real-time clock that was available in the 70s. I think I'll just use a barrel connector for the power. We really did love our barrel connectors back in the old days. I want to keep this in the 100 millimeter by 100 millimeter board size to get the lowest possible board prices on them. You can always get the $5 or the deal on JLC PCB for 5 boards for $2. So if you throw these in with an order, you can get boards for 50 cents a piece. So I guess I've actually got quite a few decisions to make, but none of these are really critical. Any of these displays would look absolutely gorgeous with this ceramic F8. So as I mentioned before, this is a back burner project, and I have boards that are due back from JLC PCB at any time. So this project may get interrupted when they come in. I'm going to try and get as much done before those boards come in. But I'm going to probably jump back on one of those projects depending on where we are in this one. The thing about spacing out board orders nowadays, the shipping has gotten so expensive that I space out board orders, but the problem is that when they come in, I've got a lot of projects in that, and I have to decide which one to pick up first. And, it's like the Love and Spoonfuls song, did you ever have to make up your mind? Hopefully, what I'd like to do is get this board off before I drop this and pick up one of the other boards that's coming back in. So hopefully I can get that done. As always, this channel is entirely fueled by likes, sharing, subscribers, and engaging comments. Okay, let me know your thoughts on this, and I will talk with you later. Bye-bye.